In this second part of our discussion of the cardiovascular system, chapter 12 in our human physiology textbook, we're going to talk about blood pressure, flow, and resistance. Now last time you may remember we were talking about the white blood cells and platelets. We had previously mentioned a lot about the red blood cells, and this slide probably fits better with that section. It's talking about chemical signals that trigger formed elements being produced in the bone marrow. So erythropoietin, as we learned, is the hormone that comes from the kidneys when they become hypoxic, causing more red blood cells to emerge from the red bone marrow. And it turns out that inflammation leads to the production of chemical signals by macrophages and other activated white blood cells that triggers the production of lots and lots of white blood cells from the red bone marrow. And so when you have an infection in your body, you'll have a large increase in the circulating white blood cells, typically neutrophils. That's called leukocytosis. So colony-stimulating factors of various types and also interleukins are cytokines that are released by white blood cells that trigger the synthesis of more white blood cells to help fight infections. All right, so let's look at the vascular system and the circuits through which the blood is pumped by the heart. The left heart is the heavy-duty major muscular pump that pumps blood through all of the capillary beds of your body. So the left ventricle pumps blood out through the aorta and then through branching arteries to all the capillary beds, virtually. This represents all the capillary beds from head to toe. It's sort of misleading because it looks like we're talking about downward movement of blood from the heart to the lower parts of the body, but really it's just meant to be symbolic of all of the capillary beds. So that rich oxygenated blood goes through the capillary beds. The cells take what they need, add some carbon dioxide, and that blood goes back to the right heart through the great veins, the vena cava. The right heart pumps, the right is a skimpy little heart that pumps blood out just to the lungs through what's called the pulmonary circuit. The left heart has to pump blood under very high pressure, as we'll see why later, to move it through all these capillary beds. So the pressure in there is on the order of 116 to 120 millimeters of mercury during systole, during the contraction phase of the heart, and maybe 70 or 80 millimeters of mercury when the heart rests. That's a lot of pressure inside the arteries. That's what pushes blood through. In the pulmonary circuit, the pressures are much lower. It doesn't take as much pressure to force blood through just one organ, the lungs. And the blood then comes back to the left heart, all rich in oxygen. So the pulmonary circulation, pumped by the right heart, the systemic circulation, high pressure circulation, pumped by the left heart. Blood vessels. We'll take a look at a diagram that describes the different sized blood vessels, starting with the largest arteries, branching into smaller and smaller arteries until we reach the smallest arteries, arterioles, blood capillaries where gas exchange and nutrient exchange takes place, and then into venules and veins and back to the heart. So arteries carry blood away from the heart. That's the strict definition of arteries. And veins carry blood to the heart. It has nothing to do with oxygenation or level of oxygen content. If you look back at the pulmonary circuit, the pulmonary arteries contain oxygen-poor blood, and the pulmonary veins contain oxygen-rich blood. If you look in the systemic circuit, the aorta and all the arteries in that circuit contain oxygen-rich blood, and the veins contain oxygen-poor blood, carrying blood back to the heart. So we start out, the largest arteries nearest the heart are called elastic arteries, and they contain a lot of elastic protein, elastin, in their wall that allows them to stretch with great violence as the heart beats and then recoil, squeeze back down and push the blood through the vascular system. Smaller arteries, as the arteries branch into smaller and smaller arteries, are muscular arteries. They contain mainly smooth muscle in their wall, very thick, strong muscular walls. And then finally we get to some very small arteries indeed, all the way down to arterioles, which are less than 1 millimeter thick arteries. And then we come to capillaries. a quick note about arterioles. We haven't really defined this yet, but the bottleneck for getting blood through the vascular system, the hardest place for the blood to force its way through is the arterioles. That difficulty of forcing blood through, that's called resistance, opposition to flow, and it's greatest in the arterioles. And then we come to capillaries, where all the meaningful diffusion and exchange of nutrients and gases takes place, and then into the smallest veins, venules, and then veins, and back to the heart. There are a couple of exceptions to this arrangement of vessels, only a couple though. All of the blood from your digestive tract, your alimentary canal, starting from the esophagus all the way down to your rectum, all of that blood goes through the hepatic portal vein to your liver. Hepatic means of the liver. Portal vein is a vein that carries blood from one capillary bed to another capillary bed. So normally we have capillary beds deliver blood into veins, which goes back to the heart. Here we have a portal vein, which carries the blood from your entire digestive tract to your liver. And then the capillaries of the liver, and then back to the heart. The hypophyseal portal system, you know about that one. That's a special way of delivering blood from the hypothalamus, carrying some important hormones, down to another capillary bed of the anterior pituitary gland. So the hypothalamic hormones get to the pituitary gland by way of this portal system, going from one capillary bed to another, and then back to the heart. This is a fun diagram. It shows the blood flow in milliliters per minute through different organs of your body. And you can see there's a tremendous difference and variation in how much blood each organ needs at rest this is. And it turns out that those numbers aren't hard numbers. They're dynamically adjusted. The blood flow to any one of these organs depends on the metabolism taking place in the organ. If your heart starts to work harder and its metabolism goes up, more blood will flow through it. If a muscle in your body is called upon to exercise, to undertake some task, the metabolism will go up, metabolic rate will go up, more blood will flow through that organ. So what in the world can cause that to happen? We have to talk about some hemodynamics before we get into the answer to that question. Hemodynamics, the sort of properties of the fluid, blood, and all the plumbing of the cardiovascular system. We'll talk about pressure, flow, and resistance. Those are the important variables that affect the movement of blood through the system. So pressure, to start out with, is defined as the force per unit area of blood on the walls of the heart or the blood vessels, right? Under pressure, think of blowing up a balloon, and the larger it gets, the tighter it gets. The more you force air in there, the tighter and stiffer it gets. There's more and more force pushing outward on the wall of that elastic balloon, and that's called pressure. It's the force per unit area pushing outward. In other words, every square centimeter of that wall, how much force is there on that by the air? In this case, the exact same thing's happening. When the heart beats, it forces blood out into the aorta and the great arteries and stretches their walls by a force pushing outward by the blood on the wall. So that's pressure. The units of pressure are given in millimeters of mercury. What on earth? The reason for that is a historical device called a manometer for measuring pressure. It was simply a glass tube, a U-tube, filled with a very, very heavy, dense metal mercury. It's a liquid at room temperature, but it's extremely heavy and dense. And so if you connect a source of pressure up to this manometer, the pressure will push downward and do work on the mercury, raising up the mercury on the other side of the U-tube against the force of gravity. And the degree to which the pressure, the force per unit area pushing down now on this mercury, can lift mercury against gravity is called the pressure, and it's given in millimeters of mercury. How many millimeters did we lift the mercury? That's where those units come from, but it's force per unit area on the vessel walls. Flow is the volume of blood moving through some part of the system per unit time. If we're talking about the entire cardiovascular system and flow through that, it's usually given in liters per minute. If it's the whole system, we call that flow. the cardiac output, because the heart is pumping all of that volume per unit time out into the blood vessels, and it circulates through and comes right back to the heart. So it's going around and around. It's called the cardiac output, liters per minute. Now you noticed already in a previous slide that if we're talking about flow just in an organ, it's often given in milliliters per minute. All right, so what makes flow happen? Flow is driven by differences in pressure. If there's a higher pressure in one part of the system and a lower pressure in another part of the system, that's what pushes blood through the system. Blood moves from higher to lower pressure. It's not infinitely easy for blood to flow through the system. There's some friction involved. Resistance is the opposition to flow. How difficult is it to push the blood through the system? So here's an expression of what we've just been talking about. Flow is driven by a difference in pressure between 2 points, right? If this difference goes up, flow goes up, and so forth, and is opposed by resistance. If resistance or friction gets higher, flow gets lower, because that's in the denominator. That's called Ohm's law. The greater the difference in pressure, the greater the flow. The greater the resistance, the less the flow, and slower the flow. So what is resistance actually? And it can be expressed in this simple form. This is an expression of proportionality. There's if we want to make R equal to something here, we're going to need some extra terms in there that we decided to simplify and get rid of by saying resistance is proportional, meaning linearly related to all these things, this clump of variables. So that's what that funky symbol is. But it's really sort of like saying resistance equals these things. So these are the variables that affect resistance, opposition to flow. This character, Greek character, represents viscosity, the thickness of the fluid. Think of having two identical funnels side by side, and into one of the funnels we're going to pour some pure water, and into the other funnel we're going to pour some nice, rich, grade A New York maple syrup. And you can immediately just intuitively realize the water's going to run through that funnel a lot faster than the maple syrup is going to run through there, or honey or something like that. It's because they're much more viscous, thick. It takes a long time for them to go through. There's a lot more friction among the components of the liquid going through that funnel. That's viscosity. Length. The length of the play. If you think of this as just a physics equation representing the resistance to pushing blood through or fluid through a long pipe, the longer the pipe, the more work has to be done, the greater the resistance, the more opposition to flow. Well, in the body, the length of your blood vessels is sort of set, but if you gain adipose tissue, add adipose tissue to your body, it effectively increases this length term, and the resistance to flow, blood flow goes up quite a bit. Here's the punchline. The radius of the blood vessels. The radius of the blood vessels is inversely related to resistance. In other words, since it's in the denominator, if the radius of the vessels increases, resistance goes down. But it's not just linearly related, it's related by the fourth power in this case. Isn't that crazy? So that means that if the radius of blood vessels increases by 2, the resistance drops by 16 times. It drops to 1/16 of what it was. Or, on the other hand, if we constrict blood vessels down to half their original radius, the resistance to flow through those vessels goes up by 16 times. Wow. So small changes in vasoconstriction and vasodilation, changing the radius of the blood vessels, makes a monstrous impact on resistance to flow. And so this is just showing you an example, a couple ways to try to illustrate this. Here we have some water being acted on by gravity in this cylinder, and where there's a larger diameter output, water is flowing out very rapidly, and where we've made the diameter half as great, not only is there less water, there's way less water coming out, 1/16 as much of flow rate coming out of that smaller diameter vessel. So that's just a way of maybe illustrating that point. This is the purpose of this left-hand diagram, is to show you that it's the difference in pressure, not the absolute pressure, that drives flow. So in the top illustration, we have a P1 pressure of 100 millimeters of mercury versus P2 of 10. We have a 90 millimeter of mercury pressure difference. That's what's moving blood through that pipe. Down here we have 500 millimeters of mercury partial pressure at one end, 410 at the other end. That sounds crazy. It's like a lot of pressure. But the difference is still 90 millimeters of mercury. The same exact flow rate would result. Let's take a look at the heart. The heart is two parallel pumps. They're not directly connected together. They're connected together by loops of blood vessels, though. So let's say if we look in the left ventricle, it receives its blood from the left atrium, and that blood passes through a valve, a one-way valve called the bicuspid valve, or mitral valve. You should know those names. Those are super important names for this valve between the left atrium and left ventricle. Blood can go effortlessly down into the ventricle. These valve flaps, or leaflets as they're called, would just move out of the way effortlessly, not like in this picture. They would fall right down flat. But then when the ventricle contracts, it pushes those valves up and they kind of slap together and close, and the blood then goes out through this valve right here, the aortic valve. Generically, this valve between the atrium and ventricles is called an atrioventricular valve, or AV valve. There's an AV valve over here in the right heart too. This little valve, the aortic valve, is called a semilunar valve, more generically, because it looks like two little crescent moons right here forming this valve in the artery. How about over in the right heart? Blood comes back to the right heart from the systemic circulation and enters through an AV valve into the right ventricle. That one's called the tricuspid valve. But again, it's a one-way valve. Blood can flow easily down into the ventricle. When the ventricle contracts, blood tries to go right back up into the atrium. The valve slaps shut, and the blood can't go up that way. It can easily, though, go out through the pulmonary artery valve, or pulmonary semilunar valve, out to the lungs. Once the heart, these ventricles relax, they've built up some pressure in the arteries, right? We've stretched their walls and forced blood out there violently. And then the walls of those vessels recoil and push on the blood, and there's a lot of pressure in there. It tries to go right back down into the ventricles, but it can't, because those little semilunar valves slap shut and the blood has to go out through the arteries to its destination. The heart wall is shown in this diagram. It consists of a lot of muscle tissue. I hate the way this is drawn. It looks like a beefsteak. That's not the way that probably the fibers of the muscle cells of the heart are arranged. But anyway, the point is the pink you see here is the muscle tissue, and it can contract and push blood out of the ventricles. It's lined with some epithelial cells. So the outer lining of this myocardium, it's called, myo means of muscle, is called the epicardium, and it's a serous membrane. Serous membranes come in pairs. The epicardium is a serous membrane on the heart, so it's called the visceral serous membrane, or visceral pericardium. And then the chamber, the cavity, I should say, in which the heart is located is called the pericardial cavity, and it's sort of defined by a very strong fibrous collagenous sac in which the heart is lodged. And on the inside of that is another serous membrane. So that's called the parietal pericardium. And these two serous membranes are right in contact with one another with a layer of lubricating fluid in between. So they drew this ginormous space in here, but what they really, they're just trying to show you the difference, but there's really just a very narrow, thin film of lubricant fluid in there, and the heart can just move all around effortlessly in there without any friction. The inner surface of the myocardium is lined by endothelial cells. Same kind of simple squamous epithelial cells that line all the blood vessels and that form the walls of the capillaries. So this is called the endocardium, the inside lining of the heart. Here's a picture of the heart valves all in one shot. It turns out that, although you probably can't tell from this diagram, maybe you kind of can, all the valves are lying in one plane, the base of the heart right here. So if we were able to just slice off the atria and leave the ventricles down below and look down, we'd see we'd see a site like this. We'd see all 4 valves staring us in the face, and we'd have the atria in our hand that we just cut off the top. You can see that the bicuspid valve has 2 leaflets or flaps. The tricuspid valve has 3 leaflets or flaps, as do the semilunar valves. What if something goes wrong with a heart valve? Have you ever heard of a heart murmur? Well, a heart murmur is something that you can hear in the stethoscope because there's something wrong with one of the heart valves. The 2 general types of valve problems include stenosis, a stiffening of the valve so it can't open all the way, and blood is forced through a narrow opening at great velocity, and it produces some turbulent flow of blood that makes a racket, and you can hear it in the stethoscope. If there's been chronic inflammation and scarring of a heart valve, it'll become stenotic, hard for the blood to get through there because it won't open correctly. If you have a leaky heart valve, that's called an incompetent or insufficient valve. The movement of blood backwards through the valve is called regurgitation. So if a valve won't seal completely, blood is going to be forced the wrong way through the valve somewhat, and that's going to, again, be under very high velocity, and it's going to make a turbulent flow that causes some violence. You can hear it in the stethoscope. And whenever you hear something in the stethoscope other than the 2 valves closing, the 2 pairs of valves closing during each heartbeat, if you hear anything else, that's called a heart murmur, and it's caused by those valve defects. So we've already taken a look kind of at this diagram and all of the named heart valves. The muscle cells themselves are kind of built up on a fibrous collagen skeleton, and they're arranged kind of in a spiral formation around the ventricles and around the atria, so that when the muscle cells contract, they kind of wring the blood out of the chambers. In the ventricles, the contraction starts at the pointy tip of the heart, the apex, and pushes blood up and out of the ventricles by the action of this kind of spirally arrangement of the blood of the muscle cells. So join me next time as we embark on a further discussion of the cardiovascular system and the regulation of blood pressure.